Today on The Future of Everything, the future of batteries and energy storage. So the last 200 years has been the story of humanity increasingly running on electricity. With the Industrial Revolution, we learned how to create generators to create electricity that were used to light up cities, power electrical trains, and bring electricity ultimately directly to our homes for use in our lights, our appliances, etc. Now, this ubiquitous availability, at least in the developed world, of electricity provided opportunities for all kinds of industries to blossom, but it also created pressure to have technologies to make electricity portable so we could carry our lights around or our appliances and not have them literally tethered to our home. This led to batteries. Batteries, as we all know, are devices that store energy in a chemical form, convert it to electricity on demand. Some can be recharged and reused. Others are one-time use only. And I think it's fair to say that our reliance on batteries in the last few decades has exploded. Cell phones and electric cars come to mind immediately, but there are myriad other devices and machinery that depend on batteries and energy storage more generally. But batteries are also critical as a means for storing electricity that is produced in bursts and at times when we might not need all of it. So, for example, solar panels make electricity when the sun is shining, but we need electricity even when the sun isn't shining. Wind turbines make electricity when the wind is blowing, and of course, the wind doesn't always blow. Same with hydropower from water, generated when the water is flowing the best. We also would like to move electricity from one place to another. If the location of power generation, like the windmills or the solar farms, is not where the energy is needed, we need to move it somehow. So we all want and need better methods for storing and releasing electrical energy. And in many ways, progress depends on the creation of better technologies. Will Chueh is a professor of material science and engineering and a senior fellow at the Precourt Institute for Energy at Stanford University. Will, how did you get interested in materials for storing or even generating electricity, and what are your current main challenges?
Well, I've been motivated to pursue technology for energy largely by climate change. When I was a student, we began to see these reports on increasing impact of climate change. And I thought to myself, what could I do to help? And I recognized that the technologies responsible for converting energy from one form to another is the crucial link. And I specifically focused on the conversion of chemical energy to electricity.
Can you tell me why is it the crucial link?
Every time you change energy from one form to another, there are inefficiencies and often there are emissions. For example, carbon dioxide and other harmful chemicals. Think of your car. Your car converts fossil fuel to mechanical energy to move the car around.
Right.
And this generates emissions and inefficiency.
Okay.
And every time this happens, we are adding a bit more to our planet that we don't want to. And I devoted my career to understand how to more efficiently and cleanly convert electricity to other forms of energy and back and forth.
So that was what was driving. That's an interesting and actually surprising answer, because you could have said, well, we need better batteries to promote progress in electronics. So when we think about these issues of storage, and one of the things I mentioned in my little intro comments were, where we sometimes generate power is not where we're going to be using it. And I know that's something that you've worked on. How are we at that problem? Are we making progress, or is it still a big disconnect, almost literally?
Yeah, I think it's a very exciting time. We're certainly making a lot of progress. Let me take you through the innovations we have accomplished. So you mentioned mobility, and this is really being the number one driving force behind developing better technology for energy storage, whether it's being able to carry the internet on your phone, being able to use your computers away from your desk, and more recently, for example, to the electrification of transportation, looking at the emergence of electric vehicles. So this is all connected to mobility.
Yes.
And I think we're making excellent progress. We are seeing electric cars. All of our devices are mobile. And we have the life we have today because of battery technologies.
And I noticed that my laptop now can make it across the country with no problem.
Whereas
as a young faculty member, that was a huge issue.
Certainly, and across the Atlantic was possible, and now it's across the Pacific is possible on a flight. And this is because we have more energy-dense batteries that can last longer. However, energy storage can also be adopted at a much more massive level. For example, as you mentioned, we are at the verge of converting our entire energy system to a renewable, a sustainable one. What does that mean exactly? The cleanest form of energy that can be produced are those from the sun and wind and other forms of renewable energy sources. The problem is that these energy sources, the production of which is not continuous. Mm-hmm. The sun doesn't shine all the time, the wind doesn't blow all the time. But our demand of energy is actually quite predictable. There are ups and downs. We use more electricity during the day. We use less electricity during the night, but we use electricity all the time.
Right.
But if you take, for example, the most sunny state, say Texas, there's still periods without the sun when there's a storm and so forth. So you have this very non-steady production of electricity, but the demand is roughly the same at any given point in time on average. So you have to find a way to buffer that electricity. And energy storage technology, in their many forms, batteries is just one of such technology, is a way to equalize things. So our long-term goal here is to say, is it possible to construct a sustainable energy system that runs primarily on electricity? And this is already true today. We run mostly on electricity for many of our energy uses. But those electricity are not produced renewably.
Right.
They're mostly from burning fossil fuel, whether it's natural gas or coal. And if we want to convert it to wind and solar, and we're doing very well on that regard, the price of wind and solar are coming down dramatically, and they're becoming competitive even with fossil-based energy sources. But they're not produced continuously.
Whereas the fuel-based ones can be, if you need to, you can run the turbine all day, et cetera.
Yep.
So let's. I want to go back and do a little bit of a primer for me and maybe for other people. Can you help me understand what is the definition of a battery versus a fuel cell versus some of the other concepts you think that an educated person in 2020 should understand the basics of?
Absolutely. So a battery is an electrochemical device. So by definition, it is the conversion of electricity to chemical energy. So chemical energy, you can think of it as the energy stored in chemical bonds. For example, water stores energy between the hydrogen and oxygen. And battery works in very similar ways. So a battery is able to take electricity and convert that.
This is when you're charging it.
When you're charging it, you can take electricity from the outside and put it into chemical bonds. And when we want to use it, then you can break those chemical bonds and then release the energy electrically. So a battery goes between electricity and chemical.
Okay.
A fuel cell is very much related to a battery, and that also does the same reaction, except that the chemicals are not self-contained. In a battery, the energy is contained in your AA size battery.
Right.
But for a fuel cell, the energy may be contained in a cylinder of fuel or coming down the pipeline. So it's whether the system is closed and self-contained versus open that defines the difference between a fuel cell and a battery. But they're both electrochemical technology. I can also give another example of a non-electrochemical energy storage, pump hydro.
Pump
hydro.
Okay.
So this is referring to pumping up water up and down. So for example, if I have a dam, a hydroelectric dam, during the day I can charge the dam by basically pumping water uphill.
Yes.
Okay, so I'm using energy electrically, and I am churning a pump, and the water goes up. And at night, I can let the water flow down and run a turbine and outputs electricity. So on a macro level, it works like a battery, but it is not an electrochemical technology because the energy is stored in the difference in the height of the water,
yes,
as opposed to the bonds in the water.
And is that so? That's a great example. Is it an actual practical option as you look at creating a sustainable ecosystem?
Absolutely. Pump hydro is one of the most attractive and lowest cost options. There is no silver bullet when it comes to energy storage. We must have a range of solutions. For example, there may be a place where there is no hydroelectric dam, so there the pump hydro option is not available. In other places, battery may not be feasible because of safety considerations and so forth. So we need a range of options, and battery is one of them.
This is The Future of Everything. I'm Russ Altman. I'm speaking with Will Chueh about batteries, fuel cells, and pump hydro, all different means of storing energy for later release. So it seems to me that part of what you have to figure out in terms of, and I am driven by this statement that you made earlier, that this is really, for you and probably for many, this is all about climate change in the end. I know that one of the issues for any sort of transfer of energy is that there's a mandatory loss of energy in every transfer. And I'm sure that this is something that you think about all the time. Are there differences in these different technologies that you just described in how efficient the storage and then the subsequent harvesting of the energy? Are there big differences there? And how much of it can we engineer and how much of it is fundamental physics that we're not going to get around?
Absolutely, Russ. So maybe we can talk about what happens to the inefficiency. If I convert electricity to some other form at 50% efficiency, where does the other 50% go? Most of the time, it comes off as heat. Mm-hmm. And this is not an easy problem to deal with, even for all the heat we're generating. But more importantly, we have to use double the energy source to make the same amount of energy. So you need to utilize more. And if the conversion process involves emission, then the emission will double as well. So efficiency is what defines how much emission goes out, whether it is heat or chemicals or CO2 or otherwise. And in this case, we need to think about improving the efficiency. And here's where electrochemical technology such as batteries is very attractive. For most conventional energy conversion, like a electricity plant, burning fossil fuel, for example, burning natural gas, the efficiency is very high if the system is large.
Okay.
So you think of a natural gas power plant. Those are 100 megawatt power plant. You go there, it's a large building.
I drive past one every now and then, and they are spectacularly large and somewhat impressive to look at.
And there you can achieve quite high efficiency. When it's that large, the efficiency for a power plant is about 60 or so percent.
Okay, so 60 is a good number to think of as very efficient, which still means that 40% of the energy is being lost, as you said, to heat, chemicals, or whatever.
And roughly you have to burn double the energy in. For electrochemical technology, like batteries and fuel cell, the efficiency can be extraordinarily high, even when they're small. So if you take a look at your AA battery, those efficiency are about 90%. And they're tiny.
So when I charge it, I might put in only 10% more energy from my wall socket than what I'm actually going to wind up sticking into that battery. And that's a pretty good deal compared to my 100 megawatt electrochemical plant.
That's right. So even your 100 megawatt power plant, it is still less efficient than your few watt battery. So one of the benefits of electrochemical technology is that it can span a range of scales. And every one of those scales, you can get very efficient conversion. Not to mention, battery, because it's a closed device, it has no emission at all.
So what about does the rechargeability of batteries? And I know this is a big thing. This is what has changed in my life, I think, probably the most. Does the efficiency get lower over time with multiple recharges, or is that not necessarily the case?
Absolutely, Russ. So this is one of the main challenge of batteries is that they degrade. There is a finite lifetime. So for consumer electronics, the lifetime of a battery is roughly about 2 to 3 years with perhaps 1,000 recharge cycles.
Okay.
So for your computer and phones, this is not a problem because it matches about the time you will replace.
The lifetime of the computer or the phone.
How fast technology moves along. So that is not a problem. But for a lot of other applications, for example, for electric vehicles, it's about 10 times more. So you have to have it last about 10 years in total, and there are mandates around the warranty periods for electric cars. And for power plants or for storing energy from solar and wind, because there's such a demand on cost, you can't replace it every 2 years. There is, you want to pay upfront costs and you want to run it like a utility.
For a long time.
And that's about 20 years. So very much so, the challenge is how do we keep the same efficiency? How do we keep the same runtime for a battery as we use it? And this is perhaps one of the most difficult challenge. And this challenge must be met while satisfying two main other things. You have to make the battery energy dense. Okay, so still have to run the electric vehicle for a certain amount of miles. And then secondly, you have to also maintain the safety of the battery. So you cannot exchange any of them. So the battery challenge today is meeting all of these different requirements at the same time.
This is The Future of Everything. I'm Russ Altman. I'm speaking with Will Chueh about actually the amazing capabilities of current batteries and yet the continuing challenges in making them better. So I don't know if you've done this kind of work, but I'm sure you're aware of the work where people are worried about calculating the cost of creating the batteries versus their incredible efficiency, as you just described. When people are trying to sum up the total impact on climate, you really have to go back to very first principles. And I'm wondering if you can comment on how mature are those models, and are they starting to give us lessons about how we are doing in terms of making the net impact of battery technology positive?
This is absolutely essential topic. This is what we call cradle-to-grave analysis of batteries or any other technology for that matter. It is looking at the energy balance, so how much energy was used to make the battery, and also how much energy was used while running the battery, and then crucially, how much energy is needed to recycle the battery. So
right.
cradle to grave.
Yes. Thank you. That's perfectly what I meant.
And also is not just in terms of energy, but also in terms of emissions. For example, how much CO2 did the battery release during manufacturing? So when you use the battery, no CO2 is released, but CO2 may be released in the manufacturing and the recycling. So there's actually a lot of work happening at Stanford here to look at this cradle to grave analysis. The general sentiment is if the battery can operate for an X number of years, then there's a payback period in terms of CO2 energy. And it's largely understood that if you use your electric car for some amount of time, and I don't have the exact number, but on the order of years, then you will pay back. You will get all of your CO2 back in that sense, because every time you use the battery, you're not emitting CO2 in the use of the battery.
So this feeds beautifully into what you were saying about getting the lifetime of these batteries and the energy density to be as long as possible, because it's in the tail of the life of the battery when all of the benefits will accrue in terms of the global optima.
You pay upfront costs in terms of energy. You pay upfront costs in terms of CO2. So the longer a given battery can last, the more you get out of your initial emissions and energy use.
This is The Future of Everything. I'm Russ Altman. More with Professor Will Chueh about energy storage and the future of our electrical grid next on Sirius XM. Welcome back to The Future of Everything. I'm Russ Altman. I'm speaking with Professor Will Chueh from Material Science and Engineering at Stanford. And Will, I wanted to now go to a vision of the future. So you've really painted a nice picture of some of the technical challenges that you're working on and others are working on for improving our ability to store energy. But you made these intriguing concepts at the comments at the beginning of our discussion about, as a matter of climate change, we have to deal with these renewable sources. They're bursty is a word that I could use in terms of when they provide power. And it occurs to me that this is going to create a network of devices. And you also referred to the scales, that some of these devices will be very small, some will be very big. Can you paint a picture for how our current electrical grid needs to evolve over the next 10, 20 years? And how do you see it working at the end of that period or 20 years from now, say?
Absolutely. So in the context of the electrical grid, you're seeing increased penetrations of renewables. And because of the up and downs of renewable or variable generation, this is causing significant stress on the grid. So introducing battery or other energy storage technology into the grid is going to help buffer this up and downs. But at the same time, you can introduce these storage technology at very decentralized level or very centralized level.
Okay.
And the grid will need to adapt for that. For example, there are discussions of how to use your electric vehicle battery to balance the grid because most of the time, your car is just parked there. So there are discussions of so-called vehicle to grid in which the vehicle battery can be used. So this will be talking about tens of thousands of cars providing energy storage.
So it's net outflow from the car to the grid.
In
perhaps.
and out to
In
buffer.
and out.
Exactly. And the grid is not designed to handle that. And there are other implications. For example, what if everybody charges their car all at once? Then you need a huge amount of energy from the grid to charge the car. And how do you balance that? So you're talking about a intermittency problem both in terms of low supply and high demand. So the incorporation of battery technology is essential, but the grid currently isn't designed to take all this distributed energy storage. If you have one giant energy storage next to a power plant, the grid can handle that. But if you're talking about distributed energy storage, this is a very different story.
So it sounds like that kind of system immediately suggests networks, information technology, computational control. It's almost like a flight control problem, but it's for electrons instead of for airplanes. So where are we with respect to big data in the electrical grid? Do we have the data we need, and do we have the kind of models we need to understand how the system must work even before we try to build it?
There is now a huge initiative underway at Stanford called Bits and Watts by the Precourt Institute for Energy, where the goal is precisely that, to understand how to design the next generation of smart grid, not only in terms of collecting information, but also in terms of control. So how do you control the grid? Now we're looking at real-time control of the grid to balance, some spot with plenty of sun or the wind start blowing in North Dakota. All this have to be factored in. And then more importantly, down the road, we can also look at smart buildings. For example, can the building also accommodate the surge and reduction in the availability of renewable electricity? So all of this is being looked at in a very collective manner here at Stanford.
Your use of the word control takes on a special meaning, especially now in light of the recent fires in California, where all of a sudden, really for the first time, I heard about closing down sections of the grid for safety reasons. And I know that it was a somewhat blunt instrument. They did not have what I would call surgical precision in their ability to do some of this. And the picture that you're painting might lead to side benefits of exquisite ability to control electricity for other reasons other than just demand. So when you talk about this, it reminds me so much of another concept that I've heard about, which is the Internet of Things, where we have on the Internet, it used to be a few mainframes talking over wires, and now it's cell phones and cell phones and even people have refrigerators and little Alexa devices on the Internet. And it has a similar flavor to what you're describing in terms of being very heterogeneous, very distributed. Are there lessons to learn from the Internet, or is the Internet and the electrical grid going to become one? How should I think about the future of the electrical grid and the Internet of Things, which is obviously going to be driven entirely by electricity?
I think one of the benefit of the Internet is highly resilient because there are many points of interconnection, and this is not true for today's electricity grid. And you might remember in early 2000, there were massive blackouts because of single points of failure. So as you go into a smarter grid that is providing information at many points that allows for control at many points, then what you will get is not only a more efficient system, but also a more resilient system. And battery technology is very much central to all of this. So yes, you could look into a future in which the grid is highly resilient. You can turn part of it off or on, allocate supply and demand, balance supply and demand in a very efficient manner.
This is The Future of Everything. I'm Russ Altman. I'm speaking with Will Chueh. Now we're talking about the future of the electrical grid. And I did want to touch upon briefly the issue of security and the electrical grid. This has come up recently because there's been, as I'm sure you're well aware, stories about hacking into the Ukrainian electrical system. There's worry about the degree to which our grid is vulnerable to attack. Where are we now with respect to security, and where should we be? And will a distributed grid of the type that you're imagining, will that help or hurt in terms of security type issues?
Yeah. Let me preface by saying I'm not an expert in any of these topics. So this is what I'm learning from my colleagues here at Stanford. In terms of security, the more interconnections you have, the more exchange of information you have, the more important security is, and also privacy as well.
Right.
And this go hand in hand. And these are being worked at here at Stanford and elsewhere to look at ways to protect information, to be able to track things without violating privacy. And this is a huge concern. And yes, the emergence of a more resilient grid will come, but it will come at the cost of all these things. So that they also must be addressed simultaneously as well.
So you at this point you are not finding yourself called into security meetings about power, at least that you can tell us about?
Right, but I'm sure some of my colleagues are.
Yes. So tell me about in the common understanding of batteries. I'm just going to go back to batteries because it's so present in our lives. Mm-hmm. I'm wondering if there are new materials that are being developed that are promising quantum leaps in areas that everybody cares about, like how long their phone lasts, how long their computer lasts between charges, and also for cars where for many of us, I happen to have a commute that is exactly 215 miles, and that's the current range of electrical cars. So I'm very afraid of buying a car because it's too close to the limit of my commute. Are there new materials on the horizon that you're very excited about and that people in your field are excited about that might give us quantum leaps?
Well, as a material scientist working on battery technologies, I couldn't be more excited. What you're describing, Russ, is called range anxiety. So in principle, this can be solved by having longer lasting batteries, but it could also be solved by having batteries that can recharge faster if, for example, you have electrical chargers as prevalent as refueling gas stations.
Yes.
But you're absolutely right that in terms of the number one metrics people care about, it is the range of the electric car, how long you can use the battery for. But there are other range of things you have to also worry about at the same time because you don't want to just increase the energy density of the battery while sacrificing other aspects. Mm-hmm. So let me point to a few of those. For example, cost. You don't want to pay a lot more for
Very
a battery
fair.
that goes
Very
500
fair.
miles. You don't want to compromise safety. You also don't want to compromise lifetime. You don't want to drive 500 miles per charge only for 2 years. So there are many materials and chemistry being looked at today that can offer substantially longer range. 2x, 3x are already possible in our laboratories. But the problem is they usually suffer in the other metrics.
They trade off on these other things.
Exactly. And I cannot overly emphasize the importance of cost. The battery industry today is a $50 billion industry. In 15 or so years, it would be $1 trillion. This is a market-driven technology. People will not want to pay more for it if they don't have to. So as we develop new chemistry in the laboratory, we have to think about how to scale it up to a $1 trillion level. And this is extraordinarily challenging. So I think some of the big opportunities that lie ahead of us is precisely thinking about how to translate discoveries in the lab that have the potential to offer 2 to 3x gain and be able to maintain that as you scale the problem upward to that can, say, supply and store energy to the entire electrical grid.
Fantastic. Thank you for listening to The Future of Everything. I'm Russ Altman. If you missed any of this episode, listen anytime on demand with the SiriusXM app.